Okay, I've been making some MOSFET DC pulsing circuits. Especially I want to have these on my rotating disc inverter thing. So I got three right here. Here's the MOSFET. It's a IRF P460. It's like for 500 volts and 200 amps. You can switch really fast. I like to put a 10K resistor across the gate in the source. It makes sure that the MOSFET will turn off. Kind of double check kind of thing with that. You don't really need it because you have a driver chip down here. Sorry. And the driver chip, the far left one, is a 10K, also a 10K resistor to it. And this comes from the Hall effect, the yellow wire. And this is the signal from the Hall effect. And this like turns things on and off. The next one to it is ground. The middle one is positive. The next one's ground. And this far one is the output that actually goes to the gate of the MOSFET, the output signal. And I put a 20 ohm resistor here, 20 ohm, to kind of like deaden any weird stuff that might happen. And you could put a ferrite tube with really thin wires wrapped around it to keep away any weird harmonics and stuff, but 20 ohm resistor is okay. It's not going to be super fast. So anyways, and so that leads to the gate. And then between the Hall effect positive and that signal source, that yellow wire, you stretch a 22K resistor, and this makes it so the Hall effect doesn't draw very much current. So this is 22K going across from the positive of the Hall effect over to the signal. So, isn't that interesting? Now, the switching will be between the drain and the source. The source is the ground. This is an N-channel MOSFET, so the source is the ground, common ground, and the drain is like the power out. And then the third one's the gate. It's all pretty simple. I got all this memorized. I can put these together without looking at anything. So I got three of these, and now let's test it. I got this one over here. Basically, I have a magnet inside here. And when and here's the Hall effect wrapped in some black tape. And I put the meter in ohms and put it across the two outputs, you know, of them. So right there, that's the meter right here. If this works right, when I put this magnet next to the Hall effect, it's going to switch this MOSFET on, and you'll have like 5 or 6 ohms up here. Okay. Also, I have a 9-volt battery that feeds the positive and negative to give the whole circuit some power. So let's go. Watch this. Here's the magnet right by the Hall effect. Only one side of a magnet will work. There we go. 0.08 ohms, 0.08. No, 0.8 ohms. That's because I have the magnet next to the Hall effect. Now I take the magnet off, it goes to nothing. So this one works. Very good. Now, if you want to take the back EMF, what people call it, or the flyback, or the collapsing field energy, what you do is you have a wire coming off the drain and a wire coming off the source, which is the ground, and you put a capacitor, the ground of a capacitor, to the ground here, and the drain wire that you attached here, you put a diode, a very fast diode on it that points into the positive of a capacitor, and that capacitor will fill up like crazy from the flyback, collapsing field, back EMF, whatever you want to call it. So the drain with a diode on it pointed to the positive of a capacitor, and the ground of the system or the circuit goes to the ground of the capacitor, and the ground is also the source because this is an N-channel MOSFET. And there you go. And you could just hook this to a lead-acid battery and just let it fly, positive and negative to a lead-acid battery if you want. But it's better to fill a cap, I think. And then when the cap discharges, disconnect one of these wires so the cap is floating. It's decoupled when it discharges. And everything will be good at that, doing that. So, there's a video for the day. I hope to have these on my rotating disc converter soon. Okay, thanks for watching.